Okay, so we're beginning chapter 17. This is diffusion and exchange of gases. And so we've been speaking so far about the structure of the lungs, the mechanical forces that move the lungs, Boyle's law, and the pressure and volume of the thoracic cavity, as well as things like your capacities and your ventilation. So now we're going to shift to the cellular level and talk about the gases. We'll talk about cellular respiration, and essentially how do we have the movement of those gases across the pulmonary capillaries, basically from two forms, from the vaporized form in the air to the diffused form in a liquid. And so that brings us to speaking about diffusion and the partial pressure of the various gases that exist inside the air. So the first thing we want to review here is oxygen moves from the alveolar to the blood at the same rate that it is consumed. So if we look at the alveolus up here, we have about 882 milliliters per minute of oxygen moving into the respiratory tract. At the level of the pulmonary capillaries, about 250 milliliters per minute moves across the alveolus into the blood at the pulmonary capillary. And that matches the same rate of movement that's happening at tissue level. So the rate of oxygen movement across the pulmonary capillaries is the exact same as that movement at the level of the cells or the tissue capillaries. And the same is true for CO2. CO2, we have about 200 milliliters per minute moving from the pulmonary capillaries out into the alveolus. It's moving in the opposite direction. And the same is true down at the capillary level, the systemic capillaries, about 200 milliliters per minute moving. So that rate is matched at both of those capillary beds, okay? So that also means that arterial blood CO2 and O2 levels are going to remain pretty much constant throughout the circulatory system. So it's going to remain the same throughout the systemic circulation as well as the pulmonary circulation. And based on that, we can basically calculate our respiratory quotient. This is the level of CO2 produced. And again, it's the same at the pulmonary capillaries as it is at the tissue capillaries, divided by the level of oxygen produced or consumed. So in this example here, our respiratory quotient ends up being about 0.8. About 200 is our CO2 rate divided by 250, our oxygen rate. And that is the same here at the tissue capillaries. And so that gives us our respiratory quotient, which tells us what amount of CO2 is being produced for the oxygen being consumed. And again, that's about 0.8, which is our standard respiratory quotient. And sort of, in terms of the application of that number, that respiratory quotient, it basically tells us our metabolic weight. How fast are we consuming these gases and how fast are we metabolizing? So that can tell us about our basic metabolic weight. Let's go to our first objective here to understand the physical factors that affect the diffusion of gases in and out of our bodies, right? We're looking at both oxygen and CO2. So we're thinking about how they move in both directions, in and out of the lungs. Now, diffusion of gases happens across the respiratory membrane. We should recall the makeup of that membrane. Remember, it is comprised of the epithelial cells of the alveolus, the type 1 alveolar cells, which are epithelial cells, the endothelial cells of the pulmonary capillaries, and then the fused basement membrane. So those three structures together make our respiratory membrane, which is the diffusion barrier for our gases. Now, the factors that will independently determine how those gases move is one, the partial pressure of the gas. We'll talk about that and how that differs first. So the pressure of the individual gases that make up the air will determine how they move. The second is the solubility of the gas. We'll talk about how easy the gas can move from its vaporized form to its liquid form, and vice versa. And that will also determine the diffusion, the overall diffusion. And we'll see, for example, that CO2 is much more soluble. CO2 dissolves much easier than oxygen does. So it's going to move, more of it will move quicker than with oxygen. So we'll talk about those two factors, the partial pressure followed by the solubility, both affect the diffusion. We want to recall here first the ideal gas law. We talked about this earlier. This is the pressure times volume is equal to the number of gas particles moved n. R, which is our ideal gas constant, so that pretty much stays the same. And T is the temperature of the gas, which is also pretty much the same considering our physiology. Now we can rearrange this equation to give us the pressure, right? The pressure, rearranging this, is going to be nRT divided by the volume. And so the pressure of a gas is going to be determined by all of these factors. The temperature, which is for the most part constant, the number of gas molecules, that's going to be also determining the solubility, how many of those particles are moving, and the volume of the overall container. Okay, now let's talk a bit more about the partial pressures. What do we mean by partial pressure? Now, in terms of a gas mixture, there are several different gases in that mixture that are each exerting their own individual pressures. That is what we mean by partial pressure. So the overall pressure of a gas, for example, the overall pressure of air, we said at sea level was at 760 millimeters per mercury, but that doesn't tell us the individual pressures of all the different gases within air, right? Air is made up of oxygen, there's CO2 in there, there's nitrogen in there. So when we think about the overall pressure being 760 millimeters of mercury, that is the combined pressures of the individual partial pressures of the gases within the air. So the overall partial pressure, the overall pressure of a gas is equal to partial pressure of gas one, partial pressure of gas two, gas three, etc., all the way up to the X or N being the total number of gases within that air. It's also going to be determined by the fractional concentration of the gas. So the partial pressure of the gas is determined by the percent of that gas. How much of the overall air is made up of the individual gas, and the percentage of the total gas overall. So an example here would be the partial pressure of oxygen is equal to what percent of air is made of oxygen multiplied by the total pressure of the air itself. And that will give us the partial pressure of the individual gas. Let's look at the composition. Let's break out each of the individual gases and talk about how they overall come together to comprise the overall pressure of air. So air is comprised of 79% nitrogen. It's about 21% oxygen. There are also other amounts of gases, carbon dioxide, about 0.3%, 0.03%, excuse me, of carbon dioxide, and then other trace amounts of things like helium, argon, and many other gases like hydrogen, neon, etc. So a lot of other trace amounts of gases besides nitrogen, oxygen, carbon dioxide will help to determine the overall pressure of air as they are helping to comprise that air. Water is another factor, especially if the air is humidified, right? Which we know that it is, especially coming through the conducting zone where it receives a lot of that moisture and is much more humidified. So water, partial pressure of water will also help to contribute to the overall pressure of the gas if we have humidity within that gas. So here's our example, the overall pressure of air being 760 millimeters of mercury at sea level, and that is owed to the partial pressure of nitrogen, which is about 0.79. That gives us a total partial pressure of 600 millimeters of mercury, plus the partial pressure of oxygen, about 0.21, because that is the percent that it's comprising, multiplied by the overall pressure of air, which is equal to about 160 millimeters of mercury. And then carbon dioxide being a very small trivial amount, about 0.03%, of carbon dioxide. Now let's consider that water. So we did describe earlier how water exerts its own partial pressure if the air is humidified. So at 100% humidity, water will also contribute to that partial pressure, to the pressure of the overall air. So the partial pressure of water is about 47 millimeters of mercury. So we have to add that into our equation as well. So looking at the composition of air, now that it is humidified, again, it's 760 millimeters of mercury combined. How do we break that out? What is the breakdown of that 760 millimeters of mercury? So that's going to be water, which is 47 millimeters of mercury, plus partial pressure of nitrogen, about 563 millimeters of mercury, plus the partial pressure of oxygen, 149, and then the partial pressure of CO2 at about 0.21 millimeters of mercury. So based on our equation that we described in the previous slide, the percent of the gas multiplied by the overall pressure of the air, we can deduce the individual partial pressures, and then all we have to do is simply sum those partial pressures of the individual components, and that should equal our 760. Now, adding these up, that actually gives us 759, which is very close. And then the rest of that is owed to the remaining partial pressures of things like helium, argon, the other trace metals, or excuse me, trace gases that are found within air as well. So 759 being the majority of that air and then very small amount to the other trace gases. So that is our partial pressure, right? That is the first factor that affects diffusion. What is the partial pressure of the gas? We'll talk about the gradient later on, but the partial pressures exert their own partial pressure gradients that allow the gases to move from a place of high partial pressure to low partial pressure, which overall drives the oxygen cascade, which is what allows gases to move through our blood. Okay. The second fact that affects diffusion is the solubility of the gas. So that is what we'll move on here to describe. What affects the actual movement of the gas from its vaporized form to its dissolved or liquid form? So first, we want to think about gas being able to exist in both of those forms. It can exist in a vaporized form in the air, or it can be dissolved into a liquid and exist in the liquid form. And the ability to dissolve is determined by the properties of the gas and the properties of the liquid. Now we want to think about those properties as the partial pressures. So both in the vaporized and the dissolved form, each of these gases will exert their own partial pressures. And when those partial pressures are the same, when they become equal, that is when the gas is at equilibrium, okay? When they're not equal, now we have a gradient and the gas itself will move from a place of high partial pressure to a place of low partial pressure. But that movement is what we describe as the solubility. How easy is it for the gas to move from its vaporized form to its liquid form and to dissolve into that liquid, and in our cases, to dissolve into the blood? So let us think about Henry's law here. And Henry's law tells us the number of the molar concentration, right? How much of that gas is actually dissolved. And that is what helps us determine the solubility. So Henry's law here, C being the molar concentration of the dissolved gas, K here representing our Henry's law, again, our constant, and then P equal the partial pressure of the gas in the atmosphere. All right. So Henry's law is another one that helps us determine the concentration of dissolved gas, which tells us about our solubility of that gas, the ability of that gas to move from the vaporized form to the dissolved form. Now, when we compare two of our common gases that are in air, oxygen and CO2, we can look at how their solubilities differ. So at 100 millimeters of mercury partial pressure in water, we're going to see that 0.15 millimoles per liter of oxygen is dissolving, while if we compare that to CO2, much more of that CO2 dissolves, right? 3 millimoles per liter of CO2 will dissolve into that water. So this simply tells us, just comparing oxygen and CO2 at the same partial pressure of water. So they are both at the same partial pressure, and more CO2 moves from the vaporized form and dissolves into that liquid than oxygen for the same partial pressure. So that overall tells us CO2 is more soluble than oxygen in water. And again, for our purposes, we want to, apply that to our physiology, and this would be in the blood. So oxygen moves, or CO2 rather, moves easier, is more soluble, dissolves easier into our blood than oxygen does. Okay, let's describe that here again. So kind of illustrating that same point, the solubility differences between oxygen and CO2, with CO2 being much more soluble. So let's look at our scenario here on the left. This is our beaker of water exposed, and we want to consider that the amount of oxygen in the water to begin with is 0, and it is exposed to air at 100 millimeters of mercury in terms of the pressure of oxygen. And then if we leave that container exposed, we should begin to see diffusion of those gas particles into water, moving from their vaporized form in the gas to their liquid form in the air, in the liquid. Now, in the ending scenario, we should see the vaporized form of oxygen, again, dissolving, and the number of molecules that ends up dissolving, again, how Henry's law here, how much of those, um, how many moles of the gas end up dissolving into the liquid form after being exposed to that air. And here we can see 0.15 millimoles per liter dissolve into our gas. And now our gas is at equilibrium. Partial pressure is of oxygen being at 100 in the air, partial pressure at 100 in the liquid as well. And only 0.15 millimoles per liter ends up dissolving into. And comparing that here to the same scenario, same sort of experiment set up for carbon dioxide, we have our beaker exposed, no carbon dioxide to begin with in the water. It's exposed to carbon dioxide with a partial pressure of 100 in the air. And then when it reaches equilibrium, the gases are now equal partial pressures. So partial pressure of CO2 in the air at 100, CO2 in the water also at 100. And now it's at equilibrium when we no longer have any movement. How much of those CO2 molecules end up moving into their dissolved form? And that is much more. It's actually twice as much as we saw with oxygen at 3.0 millimoles per liter. So twice as much CO2 dissolved into that water, to its liquid form, as we saw with oxygen, which again tells us CO2 is 2 times as soluble as oxygen.